It's great to have a chance to talk on some of the research and things that have been going on at NREL. Uh, let's hop right in here. And obviously, the trick to getting questions at the end is put in some debatable numbers. So we'll see what the questions look like at the end here. So I'm going to summarize some things here, just give you a real quick intro on what's going on at NREL recently. Just pause for a moment and talk about some perspectives on the transportation system and infrastructure and things like that I think are important to kind of put in perspective. The two core things I'll talk about is occupant comfort and how that impacts the consumption and performance of plug-in electric vehicles. I'll talk about the grid integration opportunities that we have that come from having vehicles plugged into the grid, and then we'll kind of summarize. So NREL is a national laboratory, one of DOE's national laboratories. We are the only national laboratory that is actually centered and focused on advancing renewable energy technologies and energy efficiency technologies. And we have about 2,300 employees now. It's been a huge growth period. And the real focus there is building upon this cleaner, more sustainable world by tying into industry. At the lab has always made it a priority that we have to find a way to tie in with industry so that technologies that are researched and developed in the lab find their way into industry so that they can actually make an impact. Some of the technology pictures along the bottom, wind turbine technology, biofuels research are major pieces. The building in the middle is actually our newest building on campus. It's a research support facility that houses, I believe, about 1,500 people right now. It's a LEED Platinum building, I believe, and very innovative technology in terms of office space and things like that. And then the last picture is the piece I actually work on with it, which is our plug-in electric vehicle fleet. And showing how we can recharge those vehicles tied in with renewable energy. So here's a quick snapshot. It's very detailed, but it's trying to show the complexities of what probably or what may happen, what should probably happen in terms of our transportation options and the energy and the technologies that kind of feed into that. And so if you start sort of from the left-hand side of this picture, you see that we've got this nice gray road with lots of internal combustion engine vehicles, and that probably will continue throughout our time span. While there's petroleum available, we'll have combustion engine vehicles. We started off the path with electric vehicles in the past. It kind of diminished for a while, and now really where we're sort of in this transition phase of HEVs being the main adopting technology. We're branching off in the middle there with plug-in hybrid electric vehicles. And then, we've got the fuel cell ones written off to the side. That was originally a DOE focus area where fuel cells would come in, kind of went in question for a while, but now obviously industry has picked up the ball on their side and tried to make sure that fuel cell vehicles make it through the time frame. The two other pieces, the top and the bottom of here, battery technology. Obviously, all of these technologies, not one of them is not a hybridized system other than the ICEs at the bottom, and maybe those may be even mild hybrid type technologies. Battery technology, whether it's high power, high energy technology, there's going to be a need for a suite of energy storage technologies. It's not just one chemistry. Yes, today we're talking about lithium ion technology. Tomorrow it could be a different technology. And then on the bottom, alternative fuels. It will not be entirely just gasoline or just diesel now. As we build out this infrastructure, we think about the synergies between the different fuels and how we can find a way to make it so that there is some flexibility in the system so that as disturbances with petroleum supply or whatever the conditions may be, that there is flexibility to accommodate our transportation needs with the fuel resources we have available. When you talk about the challenges and opportunities with electrifying our transportation technology, the one that really has kind of held strong and been there is really what the value proposition is of this new plug-in hybrid technology. That's kind of where we started off trying to talk about how we can displace fuel with bringing electricity to these vehicles. But the battery costs, the technology costs, the implications of the infrastructure costs, what value are we really delivering to the customer? And if you're not delivering to the customer, how do you offset those kinds of costs? The other piece that nobody's really talked about is the time to make the transitions to these technologies. Vehicles, typical average lifetime of a vehicle is about 14 years. Sales, these in the last couple of years have been off. So it is a very slow transition time to introduce new technology and get it through the automotive markets. In general, that's about 20 years from the time it's introduced to the time it's fully mature and in the industry is about 20 years of transition time. You saw those petroleum curves from the other day. 20 years means we're in a very different petroleum situation. The other two pieces up there is integration with smart grid and renewables. There's major state incentives and pushes to move towards renewable technology in our utility grid. That causes challenges. We also have smart grid technology that's coming on board that gives us communication that hopefully helps us deal with the challenges of high penetration renewables and new electricity loads. The other challenge, obviously, is uncertainty. Uncertainty is a risk factor that we all have to account for. If there's ways that we can do systems design to reduce the uncertainty is very valuable. So let's talk a little bit about passenger comfort. We all like to have our air conditioning. We all like to have our heat in our vehicles. And for the last 50 years, 100 years, we've been very lucky to have combustion engines on board that want to get rid of heat and have extra power to drive our air conditioning systems. As we move to more efficient vehicles, hybrid vehicles have these same things. We've seen it already in terms of how air conditioning and heat can affect your performance. Electric vehicles are one step further in the efficiency path, and the impacts are even greater. So this is one example published by some folks from Mitsubishi on their own IME vehicle. And the far right picture, or far left picture there is basically driving range on a full charge of electricity without any AC or heat. And then when you move to their different settings of Eco and Max with heat and with AC and heat, we're dropping from 35% down to almost 68% reduction in range. That's a huge thing that consumers will have to figure out how to deal with on their, how to re-gauge what really is their performance of their vehicle. Now, there are ways to do things about this. So we took on the role to do a simulation study. This is all modeling results that I'll talk about, computer modeling, where you can take plug-in vehicle technology options, and now that we're plugged into the grid, what's our opportunity for preconditioning the vehicle with electricity from the grid to enhance the range capability of those vehicles so that we're not losing all of that range. The flip side of that, the second bullet arrow on there is battery wear and life. So temperature, the time that a lithium-ion battery spend at high temperature is an accelerated degradation factor for batteries. You will lose life over time if your batteries sit at high temperatures. So the concept here again is if we can precondition the cabin, keep it comfortable, keep it cool for the person or the battery, we get passenger comfort value, we get battery life value. So we'll talk just a little bit about the results in here. Here's a few comparative graphs of what goes on around the country in terms of time at temperature. Picked out 4 different cities, Honolulu, San Francisco, Boulder, and San Antonio. The way to read this chart is, the numbers on the chart basically is how many hours you've spent above that temperature level. So for example, the highest temperature in San Antonio is up in the 35 degrees C period, but you're only there for an hour out of the year. The other side of the chart, obviously you're always above minus 20 in Boulder kind of temperatures. The idea being that the amount of time you spend tied into the grid to provide preconditioning or battery thermal conditioning will vary by the state region where you are. Utilities will have to figure out how to handle these kind of new loads. It's a new air conditioning on the system. Here's the quick snapshot of the spectrum of the study that we did. We looked at 3 different vehicle platforms. These are, again, simulation results, so the numbers, the type, the characteristics of the vehicles are based on published information. We're assuming that you use heat or AC when you're above 35 degrees, heat when in a condition where it's -6 Celsius degrees, and no conditioning when you're in a 20-degree case. And so those are kind of our base conditions. And then cases with and without preconditioning. And we'll look at the range impacts and battery wear attributes. This is graphically what's actually going on throughout that 24-hour period with your battery pack in the vehicle. So the top chart here is battery characteristics, battery temperature. These lithium-ion batteries want to be around 35 degrees C in their normal operating ranges. And so what we've done here is the green line is preconditioned case. The blue line is where we don't have preconditioning. And so the blue line rises up while we drive, we heat up the battery, and then it rests down to whatever the ambient condition is. In the green line, we're actually preconditioned. We're cooling the battery pack down, cooling the cabin down to a more comfortable state. It rises back up when you're driving, but it doesn't rise up as high. And so it rests back up to a thermal state. And the bottom chart is basically the state of charge of the battery over that 24-hour cycle. And I'll talk later on what the grid or what the electrical load characteristics look like from similar type of case. So here's what the summary of the results were. This was all in a published paper recently at EVS 25. And so the cases here, we've got the 3 vehicles across the bottom. We've got the charge depleting range is the measurement factor there. On the left-hand side is the air conditioning case. On the right-hand side is the heat case. The blue bars are basically the baseline, no climate control. The red is where you use that conditioning. And our assumed conditioning is as soon as a vehicle comes on, a typical air conditioning system has a ramp-up characteristic. It brings the temperature down as fast as it possibly can, and then it comes to some steady state point. What we've done is said, okay, that ramp period gets pushed off into the grid case, and the steady state period is all you maintain throughout the period. So we still have a range degradation in our preconditioning case because we're still maintaining comfort. We just don't have to do that rapid 20-minute drop in temperature or increase in heat. It was it's again similar to what those numbers from Mitsubishi were. It's about 30% drop from the no conditioning down to having auxiliary loads on. And we gain back about 5 to 15% of our range back.